Okay, so this presentation is about psoc and psoc 6. What I'm going to do is talk just a little bit about psoc and the psoc families, and then talk more about psoc 6 and what psoc 6 has to offer. psoc 6 is the latest version of our psoc, so that's why I want to talk a little bit about that specifically. Now, a lot of people don't know all the different things that Cypress does, and we do a lot of different products, not just psoc, but we have a lot of different products that address the different embedded solutions. We have products for the USB, we have products for Wi-Fi, we have Bluetooth. We also have a lot of memory products. Cypress was founded as a memory company. And not only do we have SRAM, but we have non-volatile memories such as NOR, NAND flash, FRAM, NVSRAM. We have analog components. We have capacitive touch components, and we have called psoc, programmable systems on a chip. All of these components that I talk about here supply the embedded solutions or available for implementing different things in an embedded system. psoc in particular comes in multiple families. There's a psoc 1 family, a psoc 3, 4, 5, and 6. psoc 1 was the first family that came out, and then followed by 3 and 5, later followed up with 4 and now 6. The difference between the different psoc families is a couple of things. One, the processor. psoc 1, we used a small little 8-bit micro, which we call the M8C. It's also common in some of our USB parts. psoc 3 is another 8-bit micro, but a little bit more horsepower. It has an 8051. psoc 4 has an ARM Cortex M0 32-bit processor. psoc 5 has an ARM Cortex M3 32-bit processor. And then psoc 6 is a dual core, comes with an ARM Cortex M4 as well as an ARM Cortex M0 all in one package. Now, psoc 6 does have a couple of options where you have a single core M4, but it also has the dual processor. There are other changes too besides the processor. Besides psoc having 8-bit micros and the 32-bit micros, that's just the processor that's on there. There are a lot of other things that really make up psoc. psoc is we call it psoc is a programmable systems on a chip. So even though it has the micro on chip, we categorize them by micro. It's really the connectivity that each one has. All of these parts have some amount of peripheral for serial interfaces like USB or I2C or SPI. There are other capabilities of each of these parts in terms of how much analog capability they have and additional digital capability that they have. And that's what really separates psoc from other processors. It's that analog capability, that digital capability, and the different connectivity that we have. All the psocs have on-chip flash, so there's no serial EEPROM or anything like that that's required. There are also, all of these parts have on-chip clocks. So it has on-chip low-speed clocks and on-chip high-speed clocks. Most of these parts have what we call CapSense, capacitive touch sensing. So you're doing something like a finger touch or slider or even liquid level detection. We can do that with these psocs. Now, what really is a psoc? I mentioned some of these, but this diagram shows you what they are in a little easier to follow form. Again, this particular diagram that I'm showing you is a psoc 6, but it's very similar for all the different psocs. We have a processor, and again, in this case being a psoc 6, I'm showing you the ARM Cortex M4 and the M0. Again, if there's a psoc 3, this would be an 8051. psoc 5, this would be an ARM Cortex M3. As on-chip memory, like I mentioned, and depending on the family and depending on the part, will dictate how much memory there is. All of these parts have flash. They all have SRAM. In the case of the psoc 6, it goes up to 2 megabytes of flash. In some of the other parts, it'll be less flash. Again, some of the other parts would be targeted for maybe smaller applications. We have blocks up here. We call it the programmable analog blocks. And this is what really makes psoc different from other processors. We have on-chip op-amps. We have on-chip comparators. Okay, and we have on-chip D to A converters and on-chip A to D converters. We also have on-chip analog muxes. So we can route pretty much any pin to any of these op-amps or comparators or ADCs or DACs. So you can create a real analog system all on a chip. We have a good complement of timers, counters, PWMs, and in this case here, showing with the psoc 6, there are 32 of those. There's quite a bit of timers, counters, and PWM resources. We have communications blocks. Whenever you see this block that says SCB, stands for Serial Communications Block. These can be UARTs, they can be SPI, they can be I2C, and they're all independent. They can mix and match. It doesn't matter. Those blocks can be set up in any of those combinations. Then we also have this other block here called a UDB, Universal Digital Block. Universal Digital Block allows you to implement a lot of different digital functions. If you needed additional timers and counters and PWMs, you can implement it in the UDB. If you needed additional serial blocks, you can implement it in the UDB. If you needed something unique, if it was a unique interface, you can use the UDB to implement that logic in that block. If you needed something simple, like something that was like a CPLD, where you have combinatorial logic or sequential logic, or you needed flip-flops, you can also use UDBs for that. So a UDB, something like this. A UDB you can think of as a little micro engine where we have FIFOs on chip, we have data registers, we have accumulators, and an ALU. So you can think of this as a little 8-bit slice of a micro. It has control store that'll run it. We can couple these together to make wider data paths. So even though these are in 8-bit slices, we can make it into 16-bit, 24-bit, 32-bit, and so on. In addition to this little micro engine, which we call the data path, we have PLD logic. This is the same kind of logic that you would see in a CPLD. They're equivalent of 8 macro cells per UDB, and it's broken up into groups of 4. And in this case here, again, you can do anything like AND gates, OR gates, flip-flops, and you can write code in Verilog to take advantage of these macro cells and to instantiate this data path to, again, create a logic block that's very unique, or give you something in addition to what's already part of the standard library. In our library, that's in a tool called psoc Creator, we do have low-level functions in our schematic capture. So if you wanted something like an inverter or an AND gate or a lookup table, you can just drag and drop those components onto a schematic sheet, connect them up, wire them up just like you would in a wiring tool, and then the code will automatically get compiled and targeted into that PLD block. Out of all the psocs, and I mentioned psoc 1, 3, 4, 5, and 6, there are 2 different psoc families that are of note. There's the psoc 4 and the psoc 6. psoc 4, I show you right here a roadmap or a portfolio of the psoc 4, and it's made up of what we call psoc 4000, a psoc 4100 series, a 4200 series. Then we also have what we call a psoc 4A00, which we tag as an analog coprocessor, but still very similar to these other psoc 4s, perhaps with a little bit more analog associated with it. We also have additional psoc 4s coming, There's one that satisfies the inductive sensing psoc. And again, that's in a 4. Now, what's different between all of these different psocs? Well, it really is the size. They are all arm cortex M0 parts, vary by the amount of analog that's on chip, by the amount of digital components that are on the chip, how much memory, how much I/O. We break them up into different series. Some of the PSOC 4s come with Bluetooth low energy on chip. And then we also have ones we call the S series, M series, and L series. You can think of this as small, medium, and large, because the S series are generally the smaller PSOCs, but they have fewer I/O, fewer memory, something that's really for the cost-sensitive types of applications. Medium gets you a little bit more I/O, more memory, more peripherals. We'll have things like CAN will be in the M series. And then L. L is, think of that again, as the little larger one, where it's a larger part, a bigger part, more I/O. It will have more memory, and it even picks up more peripherals. In this case, it have CAN and USB on chip. Here's an example of a PSOC 4200M series part. Again, based on the ARM Cortex M0, and all these M0s can run up to 48 megahertz. Some of the parts, again, depending on which part that you want to use, can run at slower speeds or be set as a 24 megahertz part, but they're in the family, they'll run up to 48 megahertz. Again, on-chip flash, on-chip SRAM, on-chip serial debugger uses an SWD interface, which is a standard ARM interface for programming and doing debug. The M series, as I mentioned, has the CAN for automotive, real-time clock. Many of the PSOCs have DMA, so you can offload a lot of the functionality of the processor using DMA. Let's see. These blocks here in the middle uses or has the analog blocks. So you have the op amps, the comparators, and in this case with this PSOC 4200M series, it has 4 op amps and 2 comparators. And you also see an ADC and then a couple of DACs, and then the CSD block that you see in this upper middle is for the capacitive touch sensing. The bottom middle is the programmable digital blocks. Here we have, working from the bottom up, the LCD driver. These have built-in segment drivers to drive glass directly. And one thing I should point out about the segment LCD driver, one of the issues that people have when they're using an LCD display is they don't know what the pinouts of the LCD is until they get it back, particularly if it's a custom glass. And if they have a fixed pinout on the processor, then the board has to adjust for the difference in wiring between the two, and you may have with a lot of different vias, but the routing can be very difficult. What's nice with PSOC is the IOs are very programmable. So once you get your custom glass back, and you know what your pinouts are for your LCD, you can adjust and rearrange the pins on the PSOC to drive the glass directly to give you straight shot lines and makes your wiring on your board a lot easier. And in many cases, that may allow you to have fewer layers on your board and still achieve your routing. The next block up is the SCB, Serial Communications block. Again, that's where you would have UARTs, I2C, SPI blocks, and again, those are all independent blocks. You can, in this particular case, the PSOC 4M has 4 of these, so you can have 4 I2Cs, 4 SPIs, or a mixture, an I2C, a SPI, and a UART, and another SPI. It's mix or match. They're all independent, and you can even change on the fly if you really need to. The next block up, TCPWM. These are timers, counters, pulse width modulators. Again, this particular part has 8 of those, and they're all configurable. Again, it can be set up as a timer, it can be set up as a counter. All 8 of those are independent from each other in real hardware. And then in it, here you see UDBs. Again, that's the universal digital block. This particular part has 4 of those. And again, you could use these UDBs to give you additional counters, timers, PWMs, additional communications blocks, or again, anything that's just unique digital logic that you wanted to put on the part. On the right-hand side is the I/O subsystem. The I/O subsystem allows you great flexibility with the GPIOs. Each GPIO has up to 8 different configuration types. It can be a strong I/O where it's going to drive high or low. It can be an input, let's say a digital input or an analog input. We can also do pull-ups. We can do pull-downs. We can do a pull-up and pull-down, open drain high or open drain low. And all of those are on a pin-by-pin basis. You can set those up initially and have them all set, or you can also use software to change the different drive type of each pin dynamically in code. Okay. Now let's talk a little bit about psoc 6. psoc 6 is the latest psoc family that we're doing. And again, the psoc 6 has it's a dual core processor. It has the ARM Cortex M4 and ARM Cortex M0. And like all the other psocs, it's suited for IoT, particularly psoc 4 with the BLE. psoc 6 comes with both with and without BLE. So it's adaptable very much for the IoT. In fact, it was designed specifically for IoT. And you can see in this slide, we show factory implementation. So the industrial market, the automotive market, we certainly do a lot of designs for automotive with the CAN and automotive temperatures, a variety of consumer electronics, medical electronics, appliances, but we also do a lot with wearables. Now, some of these different kinds of segments have a lot of stuff in common in terms of processing capability and requirements and memory and peripherals, but some of them also require having very, very low power, particularly the wearables. So when psoc 6 was designed, it was designed to have very, very low power. So when it was designed, we knew that it had to have a low battery or long battery life, so low power, and it had to have decent processing capability. So when you think of things like the wearables, they definitely, like I said, have to have want to run on battery, but they also require a lot of processing capability to do heart rate processing and blood pressure processing. There's a lot of processing capability required for a lot of those. But even though psoc 6 was developed with having low power in mind, it doesn't mean that it's not suitable for something that is wall powered. By all means, psoc 6 is great for both battery and wall powered applications. A couple of things to point out is psoc 6, again, it has above and beyond other processors, even though it is a dual core, we keep talking about a dual core, it has the M4 and the M0, but it also has that whole complement of peripherals that I mentioned. It has the UDBs, it has the timers, counters, PWMs, it has the analog capability. So it allows you to create the system that you need to implement any of those different segments. One other big thing that the psoc 6 has And one of the big things that is of an interest to people, particularly in the IoT these days, is security. Security is a very, very hot issue because people are worried about other companies perhaps getting their IP, or they're worried about somebody coming in and taking over and repurposing logic to do something else. And in that case, we have a trusted execution environment inside psoc 6. And what that means is someone can't come in, alter your code, and expect it to run. We have, again, this is an optional feature, but we have this trusted environment where it looks at certain signatures that power up, and if something happened that those signatures don't match anymore and it was tampered with, then the code won't execute. That way, you can have confidence in your product that when it is up and running, it is running the code that you intended to have on that product. Talked about power and power being a big thing, and here's why power is low inside psoc 6. We have, again, dual core, the M4 and the M0, and these processors are capable of running independent of each other. Not only can they run independent of each other, they can also be put into sleep modes, different sleep modes. So, for instance, you can run the M4 while the M0 is in sleep, or vice versa. You can run on the M0 while the M4 is asleep if you needed to save on power consumption. But while the M4 and the M0 are running, you can see that some of the power numbers are best in class. The M4 running at 150 megahertz in what we call the low power mode is still only pulling about 5.8, less than 6 milliamps for that processor running. If you're running at a slower speed in that 50 megahertz range and using a lower power method, it's ultra low power, then you're only pulling about 1.5, a little less than 1.5 milliamps at that 50 megahertz. So you can see that those numbers are actually pretty low compared to other processors similar to this. And in this chart, you also see the same numbers for the M0, 100 megahertz and 25 megahertz for both the low power and the ultra low power. There's a couple of different modes. So besides the active mode, you have a low power active where it's actually running even lower. There are deep sleep modes. There are also hibernate modes. And again, you can see that the power consumption on those particular modes, the 7 microamps for deep sleep and 300 nanoamps in the hibernate. There are a variety of different wake-up sources for all of those. Obviously, when it's actually running, you're not sleeping, but when you are in the sleep modes, particularly deep sleep and hibernate, you have comparators that can wake up, you have GPIO that can wake up, you can even wake up on the real-time clock for all of those. So there's a lot of different options for waking up and different power modes. The whole idea with this part, along with all the other psocs, is you have flexibility. You have a lot of flexibility on how the part is running, what's awake, what's asleep, how deep a sleep do you want to go, and how do you want to wake it up. Here's another view of what's inside a psoc 6. Again, dual core, M4, M0 plus, and then the different peripherals all around the part. Now, you're not limited to really how you partition the different interfaces and which processor core that they're running on. For instance, the Bluetooth low energy can actually be controlled by the M0 or the M4, but we tend to partition the different cores and their tasks this way. The M0 is typically used for power up, used for managing security, and typically used for running I'll say the lower level stacks of the Bluetooth low energy functionalities. And then the M4 typically will run the other functions that you need for your system. tend to run, since it is a higher performance processor and also includes a floating point engine, it would tend to run all of your main functions and often connect to the other peripherals that you may require in your system. Oftentimes, too, you may require or want to use an RTOS, and we do support RTOS for this processor. And oftentimes, you would run the RTOS on the M4, and then again, the M0 would be running the Bluetooth stack and the security and that kind of stuff. There is an inter-processor communications channel that allows passing data between the two processors, both the M4 and the M0. When you're doing a design within the tool, which you call psoc Creator, you have a choice of how the two processors interact with each other. You can also select which processor sees which interrupt from which peripheral. So if you really wanted the M0 to manage, say, some of the other serial communications and just let the M4 do all the processing, that's certainly up to you in your design. But if you wanted the M4 to do the serial interface and the control and the interrupts, that's okay too. It's up to you how you partition it. But again, we typically do the M0 with the boot up, security, and BLE, and then the other functions on the M4. I mentioned security a little bit earlier. There's a lot involved with the security and how much it can do. And again, these are all up to the user of how much security that you want to add and how much you want to take advantage. But we do add in security, have the provisions in not only for boot up, but we also have encryption algorithms on chip that you can take advantage of in storing of different keys and so on. So if security is really of an interest to you, we have notes and white papers on what we do with psoc 6, and we can certainly satisfy a lot of different security-based systems and their needs with psoc 6. Here's a competitive comparison between psoc 6 and some of the other competition. And I'll just point out a few different items here. Again, we have two different types of psoc 6. There's a psoc 6 without Bluetooth, and there's a psoc 6 with Bluetooth. Really, the only difference between with and without is the Bluetooth itself. Both of those parts have the same processors, the same speeds, the same peripherals, so it's really with or without the Bluetooth functionality. But again, with the psoc 6, up to 150 megahertz for the M4, 100 megahertz for the M0. So these are pretty good processors in terms of the speed that they run. Not too many M0s that you see run at 100 megahertz. Most of them stop at around that 48 megahertz mark. Power, or active power, you can see the MCU active power where we're 22 microamps per megahertz. That's really low compared to a lot of processors that are out there. And again, keep in mind that we're not just a processor, we're a processor plus all those different peripherals, the analog peripherals, the digital peripherals, the ability to configure your IOs the way that you want it. So it's more than just a processor, but we are very, very low power and one of the best in terms of active low power. Again, there's the analog components as you see down there. There's that hardware-based security, which very few of any other processors have the equivalent of that. So we really compete against other processors very, very well with the psoc 6. Now, this is the psoc 6 with the BLE. Again, a couple other things that I want to point out. Same kind of processor power that I mentioned before, same low power for the active. For the BLE radio, again, these are now in the lower power range. We're about 4 milliamps for the BLE radio for transmit and receive. So that's in the range that's one of the better parts that are out there for power consumption on the radios. psoc 6 is BLE 5.0 compliant, and it includes the 2 megabit per second data rate for the BLE. One other thing that I should point out, this has a flash size you see in this chart of 1 megabyte. psoc 6 has several different options. We have a 2 megabyte flash option, 1 megabyte flash option, and there's also a 512K flash option. Here's a view of the psoc 6 with the BLE. Again, as I talked a little bit about before in the one block diagram with psoc 6. Again, dual processor M4, M0. You can see the amount of memory that's on this particular part. It has the crypto engines. Again, it has DMA, like one of the psoc 4s. So you can move data around in this part without using the processor. You can do memory-to-memory transfers. You can do memory to peripheral. You can do peripheral to memory. So that DMA allows you to offload a lot of processing off of the processors themselves. Again, psoc 6 with BLE has a complement of analog, which you can see in the upper middle block there. It has a couple of op amps, has a couple of comparators. It has a 12-bit DAC. This is an increase from some of the other psocs. So it's a wider DAC, has a 12-bit SAR ADC, and does capacitive touch sensing. So again, with capacitive touch, you can do the finger presses, you can do the sliders, you can do linear sliders, you can do circular sliders. You can also do liquid level detection. CapSense is great at liquid level detection. So if you want to measure something in some kind of tube or a bowl and you don't want something to wear out, mechanically wear out, capacitive touch is a great solution for that. The digital blocks, you can see where it says TCPWM. In the psoc 6, you have 32 of those. There's a lot of timers, counters, or PWMs in this particular part. To the left of that, you can see that it has 12 UDBs. So that gives you a lot of flexibility in this part in terms of implementing logic, that may be unique logic that you might have, but it gives you 12 of those. Down below that, you can see there's serial communications block. There are 2 of them, actually, 2 blocks that you see. There's one that says SCB, and there's 8 of those, and then there's a deep sleep SCB. So you really have 9 serial communications blocks. One of them will actually operate in deep sleep mode. So you can have the part in deep sleep and send a message to it over I2C and have it automatically wake up. What's nice about this part, and again, it doesn't matter whether it's with or without the Bluetooth, both have 9 serial communications, but there are many applications where people need serial blocks. They need a lot of I2Cs, or they need a lot of UARTs, or they need a lot of SPI blocks. With psoc 6, you have 9 of them on chip. That's a lot of serial communications blocks for different systems. And that's really come in handy in a lot of different designs that I've worked on. psoc 6 also has a block that's labeled I2S and PDM-PCM. These are audio blocks. So if you need to control audio, you have I2S coming in, or you have microphones. That's where these components, these blocks come into play. You have a serial memory interface, so you can connect to an external quad SPI memory, and you can run and execute code out of that external memory. And then at the bottom, you can see where we have the Bluetooth. Again, this particular part has Bluetooth, so it's a Bluetooth 5.0 part. And then on the right-hand side, you see all the GPIOs, lots of GPIOs. And again, same part, psoc 6, but now without the Bluetooth. One thing that I should point out here that I didn't point out in the previous slide is these do have USB interfaces on as well. Now, getting started. How do you get going on this? We do have on our website, www.cypress.com, there is a product page for psoc 6. And part of psoc 6 product page, you have all the different data sheets. There's a variety of application notes. There are technical reference manuals. And we have a whole series of videos where we're demonstrating using psoc 6 in its environment, how to set up different peripherals, how to connect to the Bluetooth. There are a lot of different videos for that. We have a couple of different kits, development kits for psoc. One is called the psoc 6 BLE Pioneer Kit, which you can see in the right-hand side of this page. It's on our website, and you can see the cost. I believe it's $75 US. But this particular kit is a BLE-enabled device. It has the psoc 6 BLE on the board. It breaks out a lot of different IOs. It allows you to do capacitive touch sensing. You can see there's a couple little circles and a slider, so you can do capacitive touch sensing. This kit also comes with an e-ink display, and that e-ink display plugs onto the headers that are on this board. Those headers are Arduino compatible, so if you had other Arduino shields that you wanted to plug on here and use, you can just plug in and use that with the psoc 6. We also have what we call a psoc 6 community. So again, if you go to www.cypress.com and you go to the community page, there's a whole section on psoc 6 where you can look up questions or look up articles. You can ask questions. That's all part of our psoc 6 community. psoc Creator, as I mentioned a little bit earlier, psoc Creator is the tool that you would use to implement your code, write code, do debug, that kind of stuff. That is now available on our website, which supports psoc 6. We've been using psoc Creator for all of our psocs from psoc 3 on up. And psoc 6 is a recent addition to it. But again, that's part of the standard psoc Creator 4.2 that's available on our website now. And here are a few more links to give you a lot more information. One other thing that I want to point out is in this list, we have a second Pioneer kit that we call the psoc 6 Wi-Fi-BT Pioneer Kit page. That board uses a psoc 6 coupled with one of our Wi-Fi modules. We call the CYW4343W. So that single board, that single Pioneer kit, allows you to not only do psoc with Bluetooth, it also gives you the capability to do Wi-Fi. And I think that's it for the presentation. And I'll take questions as people have them. So one of the questions is, can you explain the communications between the two MCUs? There is a bus. It's called an IPC, an inter-processor communications bus. And there are certain channels, and you can think of it as perhaps a mutex that you would have in a real-time operating system, where one processor will send a message to another processor, and that message becomes locked until the second processor picks it up, and then once the processor picks it up, then it'll be released. And it's not just a simple message. It can actually be data that goes across. It can be something, let's say an array or a single byte or something like that. But it does allow sending the data back and forth through this particular bus. You don't share data through memory directly. The memory is separated between the two processors, but we use that bus.
Hi, is everybody has more questions? So this is the time to ask questions to Ernie. Okay. Meanwhile, the people thinking the questions. Can you hear me, Ernie?
Yep, I can hear you.
Yeah. So, is there a library for the interprocessor communications?
There is. There's not a specific, let's say, component, but there is code, and I'll say there is a library that's made up of code that shows you how or tells you what commands to use to send the data back and forth. So there are tools
Yes.
there
Yes.
for that.
Yes.
Yes.
Yes. Because I think you have to manage the two processors, no? And then, for example, you told that usually the M0 is used for the BLE communication. Oh, is that right?
That's right. Typically, that's what we do. We typically use the M0 for, again, boot up, security, and BLE, and then run everything else on the M4. Now, if you think about it with the BLE, as data is coming in on BLE, it's coming in on the M0, but you wanted to get it to the M4, right? In that case, you would send up, let's say, set up an array, and that array would be the data that you want to pass back and forth, and you just define that array to go back and forth across that inner processor communications bus.
Got it. Got it. Okay. Um, uh, I uh, I have another question also. It's that I saw related to the deep sleep. Okay,
It's related to what?
deep sleep.
Oh, deep sleep. Okay.
Yeah. So I saw that on the comparison that you chose, the deep sleep current. So it's in the case of Cypress is on the average of the market, but Scilabs is much lower. No,
Okay. In the comparison,
yeah, yeah,
yeah, in the deep sleep. Yeah. So in the deep sleep, yeah, we're probably not as low as some of the others. Certainly, Silicon Labs, they're really low. And you can see against NXP and NST, they're similar to us.
yeah, yeah,
Silicon Labs is really low. Part of the reason that the smaller your geometry, and we're a fairly small geometry, that tends to hurt your deep sleep a little bit because you have a little bit more leakage current. So that's why our active power is really low, but our deep sleep isn't quite as low as you would think.
yeah,
And Silicon Labs, I'm sure that one was optimized to be really low in their deep sleep.
yeah, yeah. Okay. So, did you have any competitive problem with this specific data? Because on the other side, so we have much more speed, much more memory, much more peripherals, no? Much
Mhm.
more flexibility, no?
Right. Yeah. Obviously, if all they care about is deep sleep power and nothing else, then sure, yeah, it's going to be tough to compete with Silicon Labs with that much. However, if you think about a system and, how much does, that deep sleep really hurt you if you're, 1 microamp versus 7 microamps, you know, or if it's on a battery, how long do you still run when you're on a battery? How many more years does it give you at 1 microamp versus 7 microamp? So depending on the size of battery you're using, it may or may not matter. So you almost
Exactly.
always have to go and look at it from a system perspective because we're
Exactly.
generally not the only part in the system. So you still got to look at it from a system perspective, and then that will dictate whether, does it really matter that we're 7 microamps versus 1 microamp? It may turn out to be nothing. It may turn out to we're even less because with the silicon lab part, they may have to add other parts to get to the equivalent solution, right? So,
Okay, got it.
and
Is there another question here? Is
I see one about when you put the M4 in hibernate and have the M0 run code. Uh, it's not in hibernate, so you can, let's see, let me go back to this one slide. If you're in hibernate is I'll say a system level. So that shuts down everything. All your clocks are shut down in your code. So at hibernate, that's at a system level. Deep sleep, same thing. If you're going into deep sleep, you're stopping your code execution. You can wake up on those. But you can go into sleep modes. Okay, you can put the M0 to sleep and still have the M4 running, or you can put the M4 in sleep mode and have the M0 running, or vice versa. So you can manage power. You can shut down one processor while the other one is still running, okay, and have or take advantage of that low power. Essentially, have the M4 go, not quite zero, but pretty close to it because you can actually have it stop while the M0 is running and vice versa. So not quite hibernate, but you do have a function like that.
by the way, that's a double that I had. So when you show deep sleep there, you show
Mm-hmm.
only is so the deep sleep in hibernate. So both processors are stopped. No, if that's the case. That's will show one value for everybody.
Right. Yeah. Both of these guys, when you hear, they're both these are both system level. Yeah.
Okay, got it, got it. Okay, that now makes sense. Okay, perfect. And there is another question from Mr. Batista. Can you see the question there?
Yeah. It says, missed part of the other. Sorry for your. Oh, okay. Our PC design guidelines and Gerber files are available. We do. We have for psoc 6. We do have a hardware design guide available for that. That's an app note. We also have for our kits, for the psoc 6 kits, we do have the design files for that, schematics and Gerbers for psoc 6. And that applies to many of the kits too. We have a variety of kits for psoc 3, 4, and 5, and we tend to have schematics and Gerbers for all of those.
Perfect. Okay. So, any more questions? Okay. I think that's all, Ernie. Thanks a lot for your presentation. Sorry for the trouble to begin.
Oh,
As I
no
told
problem.
you, as I told you, we are
Guys.
yeah. Yeah, we are just new to the webinar jam, but it's a great tool. And now also this webinar is recorded, so we can get back to it and review the presentation and also our idea is to create versions in Spanish and in Portuguese also to make easier to our customers to understand these great products that Cypress has. So it's fantastic products. It's really interesting. So we want to make easier to the people here to understand and know that how to work and understand what is inside and the possibilities of this product. Okay.
All right. Sounds good.
Okay. Thank you.
Sure
Thank
thing.
you
Let
very
me know
much.
if you need anything else.
Okay. Bye bye.
Bye bye.